Good afternoon, everyone. Welcome to this RMIT Distinguished Lecture. I'm Xinhu Yu, the chair of RMIT Professorial Academy and the host of this event. So firstly, I would like to acknowledge the people of the Kulin Nation on whose unceded lands we are meeting today. I respectfully acknowledge the elders, past, present, and emerging. So before we start, let's just get through some housekeeping matters. So this is an in-person event, which will be recorded. What we do is we will have the presentation first, which is about 50 minutes, and then followed by Q&A for another 10 minutes. Hopefully we'll finish by 4 o'clock. Okay, so let's start the lecture. We are really delighted to have the opportunity to have distinguished Professor Baohua Jia to give a lecture on atom materials for tomorrow's building a sustainable future. You can see that I'm stumbled. This is actually a new term. This is the new materials. I think it's going to be very important for the future. And I was particularly fascinated by the properties, as Professor Jia claimed, that they have the film made by this material can cool the environment by 15 degrees without electricity. So what the electrical engineers doing here in the future? So that's actually a fascinating thing to see. So I'm looking forward to see how do you do it, right? Okay, so let's before the lecture, let me introduce the speakers. So distinguished Professor Baohua Jia is an ARC Future Fellow in the School of Engineering at RMIT. She is a key chief investigator of the ARC Industrial Transformation Training Center in Surface Engineering for Advanced Materials and the ARC Center of Excellence in Optical Microcombs for Breakthrough Science. Her research focuses on fundamental light and nanomaterial interaction. She is a fellow of the Australian Academy of Technological Science, Engineering, Optica, and the Institute of Material, Mineral, and Mining. So without further ado, please join me to welcome Baohua to deliver her lecture. So over to you, Baohua.
All right, thank you very much, Xinhu, for the very nice introduction, and also thank Roberta for organizing this event. It is my great pleasure to present the lecture today on Atomaterials for Tomorrow, Building a Sustainable Future. So before the start of my talk, I would like to acknowledge the traditional owner of the land on which we are gathering today, pay my respect to their elders past, present, and emerging. So without the support from my team, my collaborator, and also funding body, I won't have this opportunity to stand here. So I would like to acknowledge their support. So really coming to the topic today, so you may wonder, what is atomaterial? So this is actually the term in analogy to nanomaterial. So if you're familiar with nanomaterial, you probably will appreciate. So in the natural world, so if you look into the nano world, as you can see here, so in our natural world, the ant is pretty small. But if you look into the nano world, you will see that ant is actually a giant in this nano world. And these are the, just gave you some idea of the scale of materials. So as you can see here, so with the development of imaging technology, we are able to look into very, very tiny world, and like red blood cell in our body, and like DNA and single atom. So we're talking about the resolution of 0.1 nanometer. And this is actually the quote from Richard Freeman, the Nobel laureate. There is plenty of room at the bottom. So these are natural material after many, many like billions of years of evolution. And actually, you know that we live in this world, we depend on this natural material to help us to really face the real world challenge. But in the meantime, it might be limited, right? So these are like only available natural material. So we may want to come up with some new material that with new functionalities to help us to solve challenges. For example, the energy challenges, like the disease is very difficult to cure. And then we make our man-made materials in the nanoscale. This is also very fascinating. If you look into the scale, we actually, in the early stage, we can make like millimeter. We have this manufacturing tool, very fine. We call that precision manufacturing. But later on, with all this nanofabrication technology, we are able to pattern all this natural material into devices that is not available before. So in this case, you see that the scale is down to micrometer scale, to 100 nanometer scale. Now we're able to rearrange atom. So using this nanofabrication tool. So one thing you probably noticed that these are like naturally available material. And then on top of that, so if we are able to add patterns, add structures, we are able to make new devices with new functionalities. And then these functionality are not available naturally. And then we can come up with new solutions. That's exactly what we want to do. And then we want to really solve real world problems. So talking about, you may ask the question, why we want to do this? Why we want to make this tiny device? So if we can provide you one example, that's talking about the chip, right? So everybody work with computer chip, communication chip. And then if you look into the chips, so basically you will appreciate that originally the chip is actually on the micrometer scale. Well, actually in the early stage, like the computer is like a whole room, right? So very big. But with this reduction of the size, you see that in the past 120 years, the Moore's law is actually governing the computer speed and also the capacity. So the smaller the size of the chip, the faster the speed, and also the better capacity, calculation capacity. So this hasn't really been broken. But is there a limit? So of course, there is a physical limit. So if you look into the chip size, currently we are using silicon as our chip material. So when we reach, now this 5 nanometer is actually a commercial device. And then the 3 nanometer is coming along. So when it reaches 1 nanometer, which is being developed, so this is going to reach the physical limit of silicon. So what are we going to do next? So in particular, with the current development of AI, so you know that the computation power required is like dramatically or exponentially increased. So what are we going to do next? So that's where these Atomaterials start to play a role. So as you know that in 2004, graphene was kind of discovered by 2 physicists in UK. And then only 6 years later, they won the Nobel Prize. This has been amazing, unexpected in the Nobel Prize history because only 6 years later. The reason is, so graphene is basically a monolayer of carbon. So it has never been separated before as 2-dimensional material, so single layer of atom. So previously, we all have 3-dimensional world. Right? Everything we have is 3-dimensional. And this is the first time carbon has been separated from their bulk. And then amazingly, this graphene has so many wonderful properties, has never been coexist in single material before. So including like electrical, magnetic, optical, mechanical, thermal, and surface area. So this is not exhaustive. So there are also other good properties. As a result of graphene, so lots of people jump into this, and then people have a huge hope that graphene is going to be the next generation of silicon, and then can continue this legacy of our integrated devices. Why we need so thin? Graphene is only 0.34 nanometer, so which is very, very thin in the world. When we have this thin material, basically you are able to achieve much better performance, and also you can use less material and less energy. Therefore, you will have energy efficient device. Even you have large kind of computational or even demand, you still use a very tiny material. So the discovery of graphene is actually opened the door for all sorts of or family of atomic scale material. So this including, as you can see here, this is basically the optoelectronic properties, so like HBN, MOS, and black phosphorus. So they basically open all sorts of possibilities. It's like a magic world to us. It's all on the atomic scale, so previously inaccessible. So these are basically the kind of big picture given by these 2 Nobel Prize laureates. So in future, if we want to have different devices, we may not have like very bulky device, but instead we have different 2-dimensional materials. So each of them carry intrinsic material property. And then if we are able to stack them together and if we are able to pattern them, so think about that. This is going to be the ultimate integrated devices. Even you have multi-layer, multi-functionality. So the entire device size or thickness is still on the nanometer scale. So how cool is that? So that means you are able to shrink the size of your chip by orders of magnitude. Okay, so this is really like the big picture, very exciting big picture. So if we look into the human development history, you will notice that material development is really the driving force of our history. So for example, in the Stone Age, like all the technology is actually developed based on this central material. Okay, so like Bronze Age, Iron Age is all like that. So we want to use this technology to serve the purpose. We want to live a happy life, but in the meantime, we want to be sustainable. We want to like balance our need and also the nature kind of sustainability. So currently, we are in the information age. And then as I just mentioned that this silicon is actually coming to a limit. What will be the next material? Signature material that is going to change our life. We believe this Atomaterial is the next material because it's really, the atomic scale is much smaller than the current nanomaterials. And then the technology around it is going to initiate this Atomaterial era. And that is why we actually established this Center for Atomaterials and Nanomanufacturing, we call CAN, to not only focus on the fundamental material development, but also talking about bringing this material out of the laboratory and then using this pattern or structuring capability so that we can have device and functionalities to solve our real-world problems. So with this, we establish our center, and then within the center, we want to develop material with a purpose. So this purpose is basically to solve the real-world challenges. So, for example, how we can make material energy conversion more efficient, how we can make the chip faster, and how we can do things with like less material usage and less pollution, and also solve these biomedical problems. So there are all sorts of application need. And within the center, we have, we have different schemes. So we start from intelligent atomic material design. This is not only using artificial intelligence, but also we use physics and chemistry to guide our design. So this way, we'll design material more efficiently. So in the meantime, there will be also atomic scale material synthesis and engineering. And also because we're talking about the atomic scale, so this is on the 0. Something nanometer. And then we'll need to develop these in situ characterization tools. And also after we develop the material, you know, this structure actually adds lots of functionalities. We have people to design this material using intelligent method to enable all these functionalities. So after we design the material, we're going to come up with device, and then this device will work with industry to translate that into the real space. Of course, the industry engagement is not only at this stage. We want to engage industry from this stage because we have this purpose in mind. So overall, we would like to use this one as a gear to actually drive the innovation and then have this output, translational output at each stage of our innovation. So in the meantime, we would like to work with industry to have to enable ecosystem, and then this ecosystem will come back to the research, and hopefully we together can establish this research ecosystem and innovation system. So how are we going to do that? So one thing in our center, very unique, we call that Open Lab platform. So this platform is basically working with industry, working with government, and also all sorts of stakeholders. If they have a need, we would like to hear, we would like to listen and work to them, and work with them, and also to develop some solution from the very beginning. We don't want to, like, we develop something and then we find the application. So we work the other way around. We have an application in mind, and then we develop material. We try to solve that particular challenges and also problem. So during this process, we are going to have this training platform available for our undergraduate and also postgraduate student. So having them like have placement in the industry sector so that they can be trained as the future workforce. So in the meantime, we also have our worldwide connection and our like conference and also networking to boost our reputation. And the main aim is trying to help or facilitate the development of this Atomaterial research and innovation. So that's the overall picture. And with this, we would like to just quickly introduce the team. So we actually have our deputy director, Rachel, and also research director to lead the entire team. So you may recognize some of the faces here. So they are from School of Science and School of Engineering. Lots of young researchers as well. We basically have very proud to have like 3 distinguished professors here, and also we have 6 future fellows and also 9 ARC DECRA fellows. So as you can see that we really like have like critical mass, and then to target this grand challenge we want to contribute to. So with this, we basically focus on, we can contribute to many areas in RMIT, including like the EICs. But in the meantime, we focus on our Atomaterial and renewable energy harvesting, and also the storage and deployment. We feel that that's something we can definitely contribute to, and that's also the critical challenge every sector is facing. So this is our key focus, and I'm going to also provide some aspects on this. So with this overall picture, I hope to provide you what we do within our center, and if you're interested, feel free to contact any one of us for collaboration. And now I'm going to start to talk about what my group is doing. So basically, in our center, each CI are focused on different aspects, different research themes. My research is focusing on this photonic research using Atomaterials. This including the solar energy harvesting, flexible energy storage devices, so for example, batteries and supercapacitors. We also work on optoelectronic devices integrated with current device or miniaturized device. And also optical communication chip. So this is linked to the combs, and also intelligent sensing and efficient particle separation. So I'll highlight a few research in these directions. So really talking about the big picture of Atomaterials, but still we need to come back to the reality. So the original graphene was actually discovered by using this Scotch tape. The process was actually quite simple but very tedious. So how they did it is with this graphite, and then use this very like normal Scotch tape, and then put on the graphite and then keep peeling off. Okay, so after maybe thousands of times, you may get a graphene layer, monolayer of graphene, if you're lucky. So it's effective. It's a useful process, but it's very like consume a lot of PhD time, right? So lots of students actually spend time making this graphene. And later on, graphene was developed by using this sophisticated CVD machine. So it can be scaled up, but very difficult for example, like multi-layer of fabrication. Because in the reality, if you want to make use of this graphene or atomaterial, you need to scale them up. You cannot really have these tiny bits, microscopic level. It doesn't really work. So the key question here is how can we scale up atomaterial? And within our center, we actually focusing on a material called graphene oxide. Graphene oxide is very close family material of graphene. So if you compare graphene oxide here with graphene, you find that there are lots of oxygen-containing functional group decorated on this graphene, and then it's either so out of plane or in plane. So the key difference between graphene oxide and graphene is because of having all this oxygen-containing group, you can actually using chemical way to synthesize it. So that means you can make it in a very low-cost method and in a large scale. And after you have this material, if you use laser pulses or microwave or heat, you're able to convert this graphene oxide into graphene. So during this process, you are able to access all these individual properties between these two materials. Actually, graphene oxide is also a very useful material. So if you look into the like the optical properties, you find that this refractive index, that means how much you can manipulate light. And the other factor is the extinction coefficient. That means how much loss you have. So basically, you want this refractive index to be as high as possible, and then this loss as low as possible. And graphene oxide actually having both property, that is what we need. So in our lab, after we can synthesize this material, we still want to make that into thin film. Because as you can see here, all these optoelectronics, so if you make thin film, you are very easy to actually integrate that with the existing device. So how to make the thin film in large scale is also very simple, but we actually spent 2 years to develop this process. So basically, we have graphene oxide, and then because graphene oxide is carrying negative charge, we have a layer of PDDA, so which carries the positive charge. And then in that case, this covered, the cover glass covered with PDDA is carrying positive charge. We put that into graphene oxide solution, and then we repeat this process, then you are going to have multi-layer of stacking. So the process needs lots of like tricks to optimize, but eventually we actually quite successful in terms of making these very well organized thin films. So this is SEM image of this multi-layer, 5-layer of graphene oxide. You see that it's continuous film, and then each layer is very nicely separated. And then if you measure the AFM, you can see that each layer is about 3 nanometer. And then we can control individual layer down to 3 nanometer in a large scale. So this coating can be on any substrate. Unlike the previous case, you have to do multiple transfer process at large scale was not possible. So this is very encouraging news for us, and then we can also make that onto flexible substrate. In this case, it's like A4 size of the transparent. So basically, we look into how good this film is. We look into the uniformity. So for example, in this case, basically, this thickness is a layer number. When we increase the layer number, the roughness of this film doesn't change at all. And then in the entire silicon wafer, you can see that the roughness is about 5 nanometer. So this is amazing. It hasn't really been achieved before because this roughness directly linked to loss. So if you have large roughness, you have all the light will be lost, and all the energy won't come into the good use. So with this, another advantage of this coating method is often we need to work with this nano device, which is like this nanostructure. You see this one is a 200 nanometer. So basically, very tiny structure you can't see with your eyes. You have to use SEM. And then we want to integrate the graphene layer with this nano device. Normally, with the normal graphene, you often see this. It's like something put on top, in which there is an air gap. It doesn't really help because you want to couple the light inside this material, and then the light normally is lost in this gap. So what we really want is this conformal coating, so having a layer of graphene on top of the nanostructure, so that, for example, in this waveguide, you will have this large enhancement once you have this conformal coating of the optical signal. So very good news for us. Now we have the thin film, we have the coating, we have that in large scale. And now we have looked into the history of this development of the material. You notice that actually this like a graphene family material was there a long time ago, but it's very, very difficult to make that into controlled way, into thin film. And only until recently, so this one large scale has been developed. Now we can think about how to make good use of the material into devices. So one of the fabrication technology I'd like to introduce is actually this, we call that laser nanoprinting. It doesn't really go through the next slide. I'm really sorry. It seems to stuck. So if I go back. Sorry, it doesn't work. I may need help from Mark. Go to the next slide. Sorry about this, this interruption. But we just want to now we have the thin film. So if we could add extra functionality by patterning it into like different pattern as what you saw in my early slices. Basically, by having all these different pattern, you are able to actually enable either electrical properties or optical property. So there is a video if you could help to show. So this is basically showing how you could pattern it. There is a video. If Mark, you can help to show it. So it's here. Sorry. So this is a video. Oh, sorry, it doesn't really show the. If you. Oh, that's all right. So basically, this shows you how we can pattern it into three-dimensional structure. So in this case, as you can see here, this is basically human hair. And then using our laser fabrication tool, we call that intelligent laser nanoprinting. So this is very similar like a 3D printing, but it's in the nanometer scale. So you are able to print anything in three-dimensional in any material. So this is in a polymer material like Venus, only 9 micrometer. And you can also print all sorts of other like devices. So in this case, early stage, we can print like opera house. And later stage, there are all sorts of development in this area. So we actually been working on how to use this laser nanoprinting to improve the resolution, to make the material more inclusive, and also to like help with the speed and yield, reliability, and also the real-time result. We can actually see what happened when we do the fabrication, and then we been working on different applications. This is our patterning tool, and is readily available in RMIT. So if you would like to access it, please come to talk to us. And using this fabrication tool, we basically do the fabrication on this graphene oxide film. And then what it does is the focus laser will remove all this oxygen-containing group and then lead this graphene oxide into graphene. So after the patterning, you have graphene multi-layers rather than graphene oxide. And then you have all these good properties of graphene. So for us, people work in photonics or optics field. We basically look into two important parameters. One is called the refractive index. The other one is called the extinction coefficient. As I mentioned earlier, this refractive index basically work on how strong you can modulate light. And then the other one, extinction coefficient, is basically how much loss you have. We want to minimize that. So as you can see here, so basically this modified material enable you to have large refractive index modulation, 2 orders of magnitude than normal material, so which is quite phenomenal. And then with this, we also try to compare using this low cost and also scalable material, how good the material property is. We actually compare our reduced graphene oxide with the CVD-made graphene. We found not only the curve is, the trend is very close, but also the property, they are actually, the actual figure, they are very close. That means using this low-cost material, we are able to have really high-cost, high-quality material property. And there are 2 things for us we would like to achieve. The first one is by reducing graphene oxide to graphene. We basically can tune the optical property in a very large range. In the meantime, we are converting a non-conductive material into a conductive material. So during these courses, we can actually do a lot of different devices. I'll give you a few examples. So the first thing we thought we could do is these integrated devices. So one thing is our lens. If you know this lens kit, so basically in our real life, we actually use a lens a lot. So for example, this camera and also this microscope, or even your mobile phone. So we're actually using light focusing very, very extensively. However, if you know that the focusing property of a lens, you know that if you want to achieve really nice focus, you need to have this very fat lens because you need to bend the incident wave and then bend this wavefront into a focus. So in this case, the stronger you want to bend it, you want to focus well, the fatter the lens will be. That is why a professional photographer will always carry this very large camera, and also this microscope, very difficult to be reduced size. So what we do want to achieve is this integrated chip. So basically we want this lens to be as tiny as possible. So how did we do this? So basically we use this 200 nanometer graphene oxide film, and then we use our laser to pattern it into a very much like a phenol lens, phenol lens that can bend the light. So in this case, because the refractive index is so large, it's like 2 orders of magnitude larger than the conventional material, we are able to reduce the thickness of the lens by 2 orders of magnitude or even more. So in this case, in this 200 nanometer, we can actually focus light into a very tiny focus board, 3-dimensional, and then we can also fabricate that into a flexible substrate. So your lens is actually is stretchable, and then this is the focusing property, and then after you stretch it, the focusing property can be maintained. So with this, we now can have a system which is much smaller than the conventional system. We can actually integrate that into this chip, and then we also work with the Defense Science Australia, and then try to incorporate this imaging system into a satellite. You know that how much it costs when you have very heavy satellite when you launch it. So basically, this is enable us to do these integrated devices. In the meantime, one of the key focus of the current imaging system is try to miniaturize the device. So for example, if you look into your mobile phone, always the thickest part is actually the camera, because you will need that camera multi-lenses in order to achieve good imaging. So with this flexible lens, we are able to actually stretch it to try to replace the lens kit. So normally you have several lenses. Now we only have like this stretch. You can actually move this focus back and forth. So this is called zoom lens. And then this way we can dramatically reduce the size of the imaging system. So in the meantime, you can also integrate this lens with a fiber. So this is basically the focusing property after we integrate the lens on the fiber. So what we want to do is really to enable this very tiny endoscope, because originally if you have this like day surgery experience, this endoscope is actually quite big. It's about 1 centimeter or several millimeter, and then there has to be a significant cut for the patient. And then if we are able to reduce the size of the endoscope, and then this one is the same size of a human hair, so you are able to still achieve very nice imaging, but having this minimum invasive operation. So this is also something we are developing or enabled by this technology. So just to change the gear a little bit, we talk about the imaging, and then we can also do a lot of things in energy harvesting and also energy efficient management sector. So here I would like to show you a case of how to do this photo thermal management, so to provide some solutions that we were not able to achieve before. So really thinking about the Earth, on the Earth, we actually spend a lot of energy on managing the thermal. So you may not realize this. So for example, in wintertime and summertime, we use a lot of air conditioner. So in this case, in the summertime, when there is a high temperature in Australia, we often suffer from a blackout. So if we look into in terms of financial figures, only in 2020, in the thermal management is actually 47.5 billion. So this is a huge number, and we even don't consider like this CO2 emission and also environmental impact. So if we are able to do something like regulate the temperature without using air conditioner, so think about how good is that. So can we do this? So if we consider the normal way of doing this heat is basically, if you use the air conditioner, you basically move the heat out from the room to the outside, right? So the heat is still around. But if we look into a larger scale, okay, so if this is the Earth, and then we get all the heat from the sun. And then in the meantime, if you know that we have on the Earth around 8 to 13 micron, we actually emitting the heat to the outer space all the time. So the outer space is like a refrigerator. It's like absolute zero. So if we are able to move all the heat to the outer space efficiently, then we may not need a refrigerator or air conditioner. So how could we do this? Well, if we use conventional way, there's no way, right? So we cannot really throw the heat just to the outer space or exhaust it. But if we look into this spectrum space, it's very interesting because so when we receive the heat, it's actually in the visible to the IR range. So that's the heat we receive, and then that's the heat we gave out to the outer space. So in a very clear day in the winter, you will feel that the coldness. That's exactly this radiative cooling is play a role. So if we are able to develop something to control the spectrum, to only allow this heat coming out in the winter time, and then on the other hand, to minimize this part and then only allow the radiative to the outer space in the summertime. So we have a way to control the temperature without using air conditioner. So how could we do this? So basically in our lab, we developed this broadband absorber. So first of all, to allow the complete absorption of the solar spectrum. So this requires a material that is responding to the entire solar spectrum. Actually, graphene is this material, this very unique material. It has response even to the microwave. It has the same absorption. But only using material, using graphene, you won't have this good property. So using our laser, we pattern it and then convert the incident light into vertical propagating light. So this way, only using 90 nanometer of the material, we are able to so horizontally absorb the entire solar spectrum. So if you look into such absorption under the sunlight within 40 seconds, the temperature can increase to 160 degrees. And then this compared to the normal absorbing material is like over 100 degrees more. So basically, this is an efficient method to convert solar energy into heat. And then we can harvest the heat into other useful format. So the other, we talk about 90 nanometer just now, and then people may ask, well, 90 nanometer is still quite thick. Can we further reduce it? Yes, we can. So using like this structure design, we can actually even further trap light to avoid this black body emission, which is a loss mechanism. We can minimize that, allow the full absorption of the solar spectrum, and then this way we can manipulate the light spectrum and only allow the full absorption within this 30 nanometer of graphene. And then after that, we actually fabricate this material inside our lab. And then this is the copper foil without the fabrication of this nanostructure. And after coating this graphene layer, you can see that the absorption, it becomes really dark. And then within like also less than 1 minute, we can actually increase the temperature to about 85 degrees C under the sunlight. So this is basically the spectrum manipulation using this nanostructure. So what can we do with it? So after we have this heat generation, what can you do? So you know that on the Earth, we have lots of water, but 97% is actually in the sea, right? Only 3% drinkable water, and most of them, they're underground. So if we are able to convert the seawater into drinkable water, that would be brilliant. Because lots of people, they will be like saved, right? So they will have clean water. So how can we do this? So we developed this, we call that diurnal structure. On top of that is this three-dimensional structure. At the bottom is like two-dimensional channels. So it basically allows the seawater to come through the channel, and then on top, it converts the solar energy into heat. So it heats up and then keep like drawing the seawater into the top and then get evaporated. The evaporated water is clean water, and then this is basically the apparatus we developed in the lab. And we also try to measure the generated clean water and compare to the WHO drinking water standard. And as you can see, that is not only meeting the requirement of the drinking water, but also exceed the requirement. So that means this water is drinkable. And the good thing about it is, we developed the device as well. So basically this device is, so you just pour the seawater in, and then we have the film absorb the sunlight, and then from the other side is actually clean water coming out. So this basically generating the clean water without using any electricity, so all driven by solar energy. So producing clean water is not the end. You can also do more. But before doing this, you need to scale up the film. So in our lab, we also produce this, we call that prototype thin films, so they can be continuously produced like meter after meter, and they can be scaled up. So with this one, you can do something further. From this one, this is basically a project we're working with Southeast Water and also funded by ARENA and also ARC Discovery and Graphene X and Victorian government as well. So we can add photocatalytic material inside this photo-absorbing material, okay? So to have a monolayer of thin film. And then by having a chamber to separate oxygen and hydrogen, and then this floating device can generate hydrogen directly from the seawater. So what it does is basically to have different catalysts to enable this like solar-driven the conversion. So this one is in collaboration with Professor Ma and also Professor Han Lin. And then we also developed this catalyst by working with our colleagues. So the device is basically like a modular device. In the lab, we developed this small module, and then by organizing them into large scale, so you see that this is basically the structured one, and then this device can really floating on the sea surface, and then which is quite robust against the waves. And also, this is a show of the device. And so such a device can also generate different ports. You see that hydrogen and oxygen can be generated separately and can float on the surface of the water. It doesn't matter whether it's seawater or any like recycled water or gray water. So very exciting to see the next phase, which is the field trial. In this project, we are going to scale that up to about 100 meters square, and then we are talking about prototype or pilot demonstration in Southeast water and with graphene oxide. With graphene X. Yeah, so we talk about the heat part, right? So now we talk about the cooling part. So you may wonder how we can do the cooling part. It's actually quite simple as well. So as I mentioned, this is basically what we do. It's a flexible device. We put that into this chamber. This chamber is nothing but just aluminum foil, and it doesn't really have any active device. We have two temperatures here. One's inside, one is outside. So once we put this film inside this chamber, you see that this temperature is reducing, and then this is the environmental temperature. It doesn't really change at all. So this is a real-time measurement. Within about 10 minutes, you can see this one. There is a huge temperature difference. So the trick we did here is really we designed this nanostructure and we fabricate it into the material, and then we minimize the absorption of the sunlight, which heat it up. We don't want it to be heat up, and then in the meantime we maximize the emission to the outer space, which is between 8 and 13 micrometer using our nanostructure. And by doing this, this film is basically whatever you attach, this film will get cooled down. So, in order to make real-life usage, we actually developed this large-scale manufacturing kind of process in our lab. So this is using laser nano printing. We actually fabricate this mold, and then using this roll-to-roll printing, we develop this large-scale thin film. And then this thin film, it's very effective in terms of manipulating the spectrum. And with this, we actually quantify the result, as you can see. As you can see here. So in a clear summer day, so we can actually reduce the temperature by 8.5 degrees. And then in the daytime, nighttime, they also showed very effective reduction. And also nighttime is actually cooler, and then this temperature reduction is about 5.5. And think about that. If you have a film like this, what can you use it for? So you can basically use it for everything related to thermal management, right? So thinking about the scenario in the summertime, in particular in Melbourne, it's like sometimes air temperature is like 40 degrees, right? So if you jump into a car, you often like burned by the car seat, or you feel really hot air coming out. So if you have a car cover using this cooling film, you no longer suffer from that heat. So in the meantime, you can also think about our supply chain of the food. So we can develop this cool food container, which doesn't require air conditioner, and then that can preserve the food and make sure that we have very fresh food. So in the meantime, this one was developed during the COVID. We noticed that the COVID coat is actually very hot because you need that insulation. And then inside the coat, it could be like 50 degrees, but with our coating is about 30 degrees, so less than our body temperature. So this is really like the application. So in our case, we work with our industry partner and also our partner in Western Sydney University. We apply this film in the greenhouse. Okay, so the first generation of the smart film, we actually grow very nicely all these vegetables. And one of the key advantages of doing this project is we get lots of free vegetables to try. So it's really like the fruit from the scientific research that I enjoy. Very sweet. In the meantime, we actually monitor the energy consumption, because the key point is without using this ventilation, how much energy we can save. You may be surprised, because in the greenhouse, we're supposed to have very hot temperature, right? But actually this hot temperature is too hot, it's killing the vegetable. And then after applying the smart film, 20% of energy can be saved, and also water usage can be saved. So in terms of the cooling, the energy save is really encouraging, but we also want to get a plant yield increase as well. So with this, we're currently trialing our second generation of the film in Victoria. So this is our greenhouse. They are all identical. We actually control all these conditions. So working with industry, we're testing all the vegetables, and then we currently increasing the yield as well. So really excited to share with you. This one is actually just founded early this year. It's ARC Industry Hub led by RMIT. We have quite a few RMIT CIs on this. We call that energy efficient protected cropping. And then what we have now is everybody knows greenhouse is good. It produces consistent food, but it's very energy hungry. And in future, we would like to have this energy efficient greenhouse, which is enabled by this like thermal control and these fascinating like energy solutions that we're going to develop. And also it has the intelligent management as well. So I think on the last couple of minutes, I'll just quickly talk about another direction in terms of the communication devices, which is, you probably know this, which was founded last year, and we're going to have this official opening in October. So ARC Center of Excellence in Optical Combs for Breakthrough Science. So the key focus of this research center is try to develop an optical comb, which is a light source, to be miniaturized from meter scale into a chip, so that you can integrate that into like different communication and computation, this kind of application scenarios. So these are all the CIs within the center, and the center, as I said, is opening for recruitment. So if you're interested, feel free to talk to any one of us. Here, this Atomaterials is actually playing a very critical role in terms of enable the nonlinear property, because nonlinear property is very critical for communication device in terms of having this energy efficiency. In almost all our communication devices, we are using all sorts of nonlinear property to enable the communication speed. But normally, the naturally available material is very low in terms of nonlinearity. So using this Atomaterial, because they have their quantum confinement, even single layer of Atomaterial, they have very strong nonlinearity. So if we compare this Atomaterial with our conventional, for example, silicon, so you basically have about 4 orders of magnitude higher in terms of nonlinearity. That means you are able to use very tiny material to enhance your efficiency. So in this case, we integrate our Atomaterial with different architecture, so talking about silicon nitride, different material platform, and we found that after the integration, the nonlinear enhancement is like at least 10 dB, so which means that you're able to use less energy to achieve much stronger signal. So in this case, we are working on like different platforms, and then this performance enhancement you can see from a few dB to like over 10 dB, and some of them is even over like 15 dB. So that means a huge enhancement. So with this, I'd like to just quickly highlight, so because of time limit, I won't be able to go through all this fascinating research with Atomaterials. But if you're interested, you're more than welcome to look into the several review articles that we've been working on, we have published. And indeed, this Atomaterial enables lots of integrated devices. So this could find fascinating applications in not only like communication, but also like AR, VR, and also point of care, biomedical devices, and energy devices. So they save a lot of energy and also enhances the signal. So with these, within the combs, so we provide these devices for our colleagues. For example, in ANU, they work on combs for sensing to predict the earthquake and storm prediction and weather, like a more accurate weather forecasting, and also smart city monitoring. And also our colleagues in Swinburne is using the combs for astronomy, so really understand finding Earth-like planet, and also really understand where the Earth originates from. And my colleague in University of Adelaide is using these combs for understanding human body from the embryo stage. So really, as you can see that due to time limit, I can only give you a little bit taste of this Atomaterial. But if you would like to understand more or collaborate with us, please feel free to talk to our center member. And actually, the take-home message here is really Atomaterial is emerging, but is changing our world. It's not really in the future, it's actually happening now. So our center is hoping to facilitate this transition and also to make some contribution to find solutions to tackle the grand challenges. All right, so last minute, we have conference actually coming along in November 26th to 29th in RMIT, and then this is really our plenary speaker, very stunning team of speakers. So you're most welcome to attend the conference, and thank you so much for your attention.
Okay, thank you very much, Baohua. It's a very packed, dense presentation, but fantastic work.
You.
Any questions or comments? We got a few minutes. So.
Thanks a lot for Baohua's excellent talk and fascinating application of the atomic materials. And as we all know, the recently Nobel Prize awarded to the artificial intelligence. Do you have any plan for extending your atomic materials combined with the research correlated to the AI? And if you want, and what is your initial thought about it? Thanks a lot.
Yeah, thank you very much for the question. Actually, I was really excited and encouraged by the recent awardee of the Nobel Prize, because AI is actually planned in the center research. I think rather than just directly using AI, which is a very like computation hungry kind of approach, we would like to combine that with physical and chemistry principle to actually confine or to guide the AI design, because otherwise you only based on the data-driven, which consume a lot of energy. Lots of people saying that future AI is basically energy competition rather than the algorithm, because if you really want to design new materials, you need a lot of computational power. That is not what we would like to see the approach. We would like to have like people's understanding to guide that to make it more efficient. So that's already in the plan. I think definitely with your joint RMIT, so we can actually work more closely to make that happen. Thank you.
Thank you very much. Any more questions? Yeah, just relating to the AI, I guess you mentioned about silicon, right? You talk about we are already almost reaching the physical limitation. But I mean, the electrons travel by light, but we already reached just a fraction of speed. But in that way, I think it appears to be the graphene probably only doesn't actually improve the speed, but rather reduce the size, so you don't overheat, I guess. Is that my interpretation?
Yeah, thank you so much for the very, very good question. I think here there are like a few folds. The first thing is if we are able to reduce the size of the device, basically we make it more energy efficient because it doesn't need to travel like long way, and then this electron collision will be less. So hopefully less heat generation. That's for the integrated devices. So in the meantime, we're also working with photons rather than electron. So that's the research aim of this ARC Center of Excellence as well. So using photon to replace the electron, basically photon doesn't really carry a mass, and then it doesn't really generate that collision. So hopefully the heat, like a heat loss, will be dramatically reduced. So in the meantime, so by like optimizing the material property, making graphene is like a highway for either photon or the electron. So we make the material, the highway, as smooth as possible. This way we have less loss in that device. So that's several folds of optimizing the structure. Yeah.
Thanks.
Thank you.
So we're almost close to the end. One more last question. So if there's none, please join me to thank Baohua again for the fantastic talk.
Thank you very much.
We have we're looking forward to the attending the new the future distinction lectures. We have a refreshment outside. You can continue the discussion and networking. So thank you very much for coming. Yeah, thank you.